Let's examine the quadratic equation, open parentheses 3x minus 1, close parentheses squared, minus 25x squared equals 0. This is a special type of quadratic equation we can solve efficiently. Notice we have a binomial squared term, open parentheses 3x minus 1, close parentheses squared, highlighted in yellow. This structure gives us a hint that we might be able to use the difference of squares pattern. To solve this equation effectively, we'll follow these 4 key steps that apply to many quadratic equations with similar patterns. Step 1. We'll rearrange the equation to isolate the squared terms on opposite sides. Step 2. We'll recognize and factor the expression as a difference of squares, which is the pattern a squared minus b squared. Step 3. We'll use the formula that a squared minus b squared equals open parentheses a plus b close parentheses times open parentheses a minus b close parentheses. This is a fundamental algebraic identity. Step 4. Once we have the factored form, we can set each factor equal to 0 and solve for x. Now let's work through the actual solution process step by step. Here's our original equation. Open parentheses 3x minus 1 close parentheses squared minus 25x squared equals 0. First, we move all terms to one side. Adding 25x squared to both sides gives us open parentheses 3x minus 1 close parentheses squared equals 25x squared. Now we have a perfect setup for the difference of squares formula. Looking at this equation, we can identify that a equals open parentheses 3x minus 1 close parentheses and b equals 5x. Using the formula a squared minus b squared equals open parenthesis a plus b close parenthesis times open parentheses a minus b close parenthesis, we get open parenthesis 3x minus 1 plus 5x close parenthesis times open parenthesis 3x minus 1 minus 5x close parenthesis equals 0. Now let's simplify what's inside each set of parentheses. In the first factor, 3x minus 1 plus 5x becomes 8x minus 1. In the second factor, 3x minus 1 minus 5x simplifies to negative 2x minus 1. So our equation becomes open parentheses 8x minus 1 close parentheses times open parentheses negative 2x minus 1 close parentheses equals 0. What we've just applied is the difference of squares pattern. It's a powerful technique that allows us to factor expressions in the form a squared minus b squared, which otherwise might seem challenging to solve. When a product equals 0, at least one of the factors must equal 0. So we have 8x minus 1 equals 0, or negative 2x minus 1 equals 0. Solving the first equation gives x equals 1/8. Solving the second equation gives x equals negative 1/2. These are our two solutions. You can verify these answers by substituting them back into the original equation. For example, when x equals 1/8, the binomial 3x minus 1 becomes 3/8 minus 1, or negative 5/8. When squared and compared with 25 times 1/8 squared, the equation balances perfectly. The difference of squares pattern is an important tool in algebra that helps us solve certain quadratic equations more easily. Whenever you see expressions like a squared minus b squared, remember this factoring approach. Let's examine the binomial square formula, which allows us to expand expressions of the form a minus b squared without having to multiply everything out manually. Our task is to expand this expression, 3x minus 1 squared. We'll use the binomial formula we just saw to make this process systematic and efficient. To apply our formula, we need to identify what a and b are in our expression. Looking at 3x minus 1 squared, we can see that a equals 3x and b equals 1. Now that we've identified our variables, let's apply the binomial square formula step by step to expand our expression. First, we'll substitute our values of a equals 3x and b equals 1 into the formula. This gives us 3x minus 1 squared equals 3x squared minus 2 times 3x times 1 plus 1 squared. Let's evaluate each term individually, starting with the first term, 3x squared. When we square 3x, we get 9x squared because we square both the coefficient and the variable. 3 squared is 9, and x squared remains x squared. Moving to the middle term, negative 2 times 3x times 1. Here we multiply all these factors together. 2 times 3 gives us 6, and we keep the x. Since we have a negative sign, our result is negative 6x. For the last term, 1 squared, we simply compute 1 times 1, which equals 1. Notice that squaring a constant like 1 just gives us the same constant. Now that we've calculated each term, we can combine them to find our expanded expression. Substituting all our results into the formula gives us 3x minus 1 squared equals 9x squared minus 6x plus 1. This is our fully expanded result. We've transformed the compact form 3x minus 1 squared into a standard polynomial, 9x squared minus 6x plus 1. Each term represents a different power of x squared, x to the first power, and a constant term. The expanded form is important because it allows us to more easily perform operations like finding roots, factoring, or combining like terms with other polynomials. We've successfully transformed 3x minus 1 squared into the standard form, 9x squared minus 6x plus 1. Let's examine this quadratic equation, where we have a binomial term, 3x minus 1 squared minus 25x squared equals 0. Our goal will be to simplify this equation into standard form. First, we need to expand the binomial squared term. Remember that for any binomial a plus b squared, we get a squared plus 2ab plus b squared. In our case, with 3x minus 1 squared, we'll apply the formula a minus b squared equals a squared minus 2ab plus b squared. Now we substitute this expanded expression into our original equation. The term 3x minus 1 squared becomes 9x squared minus 6x plus 1. The rest of the equation stays the same. Next, we remove the parentheses since they're no longer needed. We can rearrange the terms to group similar powers of x together, which will help us combine like terms more easily. Now we can combine the x squared terms. We have 9x squared minus 25x squared, which gives us negative 16x squared. Notice how combining like terms simplifies our expression substantially. We've now transformed our complex-looking equation with a binomial squared into a standard form quadratic equation. Negative 16x squared minus 6x plus 1 equals 0. This is much easier to work with for solving purposes. This final form, negative 16x squared minus 6x plus 1 equals 0, can now be solved using standard methods like factoring, completing the square, or the quadratic formula. Notice that we can also divide all terms by negative 1 to get a positive leading coefficient if preferred. Let's examine our quadratic equation, negative 16x squared minus 6x plus 1 equals 0. Notice that the leading coefficient is negative, which can make applying the quadratic formula a bit more challenging. To make our work easier, we'll multiply every term on both sides of the equation by negative 1. This will give us a positive leading coefficient without changing the solutions of our equation. When we multiply each term by negative 1, we'll need to apply the rules of sign changes. Remember, multiplying a negative number by negative 1 gives a positive result, while multiplying a positive number by negative 1 gives a negative result. For our first term, negative 1 times negative 16x squared equals positive 16x squared. When two negative numbers are multiplied together, we get a positive result. For our second term, negative 1 times negative 6x also gives us positive 6x, following the same rule of sign changes where negative times negative equals positive. For our constant term, negative 1 times positive 1 equals negative 1. When we multiply a positive number by a negative number, the result is negative. And on the right side of the equation, negative 1 times 0 equals 0, since multiplying any number by 0 always gives 0. After multiplying both sides by negative 1, our equation is now transformed to 16x squared plus 6x minus 1 equals 0. Notice that all the signs have been flipped, and most importantly, our leading coefficient is now positive. Now we need to identify the coefficients in our standard form equation to prepare for using the quadratic formula. Remember, the standard form of a quadratic equation is a x squared plus bx plus c equals 0. Let's identify each coefficient in our equation so we can substitute them into the quadratic formula, which states that x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our equation, a equals 16, which is the coefficient of x squared. This is now positive, which makes working with the quadratic formula more straightforward. The coefficient b equals 6, which is the coefficient of the linear term x. This will be important for calculating the numerator in our quadratic formula. And finally, c equals negative 1, which is our constant term. This value will affect the discriminant b squared minus 4ac, which tells us what type of solutions our equation will have. Now our equation is in standard form with a positive leading coefficient. These values of a, b, and c can be directly substituted into the quadratic formula to find the solutions. By multiplying by negative 1, we've made the equation easier to work with without changing its solutions. The quadratic formula is one of the most powerful tools in algebra for solving quadratic equations. It works for any quadratic equation, whether or not it can be factored easily. Let's apply the formula to solve this quadratic equation. 16x squared plus 6x minus 1 equals 0. To use the quadratic formula, we first need to identify the coefficients from our equation in standard form. Looking at our equation in the form ax squared plus bx plus c equals 0, we can identify that a is 16, the coefficient of x squared. The coefficient b is 6, which is the coefficient of x. And c is negative 1, the constant term in our equation. Now we can substitute these values into the quadratic formula. We replace b with 6, a with 16, and c with negative 1. This gives us x equals negative 6 plus or minus the square root of 6 squared minus 4 times 16 times negative 1, all divided by 2 times 16. Let's simplify what's inside the square root. First, 6 squared equals 36. Then 4 times 16 is 64, and 64 times negative 1 is negative 64. But because we have a minus sign before the 4ac term, negative 64 becomes positive 64. Adding 36 and 64, we get 100 inside the square root. The expression under the square root is called the discriminant, and since it's positive, we'll have two real solutions. The square root of 100 is 10, so our expression becomes negative 6 plus or minus 10 all over 32. Notice that the denominator 2a equals 2 times 16, which is 32. The plus or minus symbol gives us two possible solutions. Let's work them out separately. For the first solution, we use the plus sign, negative 6 plus 10 over 32. For the second solution, we use the minus sign, negative 6 minus 10 over 32. Let's simplify the numerators. For the first solution, negative 6 plus 10 equals 4. For the second solution, negative 6 minus 10 equals negative 16. Now let's simplify these fractions. For 4 over 32, we can divide both the numerator and denominator by their greatest common factor, which is 4. This gives us 1 over 8. For negative 16 over 32, dividing both by 16 gives us negative 1 over 2. We found that the solutions to our quadratic equation 16x squared plus 6x minus 1 equals 0 are x equals 1 over 8 and x equals negative 1 over 2. You can verify these solutions by substituting them back into the original equation. From our previous work with the quadratic equation, we found that x equals negative 6 plus or minus 10, all divided by 32. Let's solve this expression to find our exact solutions. We need to evaluate both possible values of x by working with the plus or minus sign separately. First, let's solve for when we use the plus sign in the numerator. When we add negative 6 plus 10 in the numerator, we get positive 4. So our fraction becomes 4 divided by 32. To simplify this fraction, we'll divide both the numerator and denominator by their greatest common factor, which is 4. This gives us 1 over 8 as our first solution. Now let's find our second solution by using the minus sign in our original expression. We'll substitute negative 6 minus 10 in the numerator. Adding -6 and -10 gives us -16 in the numerator, so our fraction becomes -16 divided by 32. We can simplify this fraction by dividing both the numerator and denominator by 16. This gives us -1/2 as our second solution. So our quadratic equation has two solutions, x equals 1/8 and x equals -1/2. Let's highlight both answers. To be absolutely certain these solutions are correct, we need to check them by substituting each value back into the original equation. This verification is an essential step in solving any equation. Let's recall our original quadratic equation, the quantity 3x minus 1 squared minus 25x squared equals 0. We'll first verify that x equals 1/8 satisfies this equation. We'll substitute x equals 1/8 into each part of the equation. This gives us the quantity 3 times 1/8 minus 1 squared minus 25 times the quantity 1/8 squared. Let's evaluate the first term. 3 times 1/8 equals 3/8. Then 3/8 minus 1 equals -5/8. For the second term, 1/8 squared equals 1/64. Now we have -5/8 squared minus 25 times 1/64. Remember that when we square a negative number, the result is positive, so -5/8 squared equals 25/64. For the second term, 25 times 1/64 equals 25/64. So our equation becomes 25/64 minus 25/64, which equals 0. The left side simplifies to 0, which matches our right side of 0. This confirms that x equals 1/8 is indeed a solution to our original equation. Now let's verify our second solution by substituting x equals -1/2 into our original equation. We'll replace x with -1/2 in both parts of the equation. For the first part, 3 times -1/2 equals -3/2. Then, -3/2 minus 1 equals -5/2. For the second part, -1/2 squared equals +1/4. Now we have -5/2 squared minus 25 times 1/4. Squaring -5/2 gives us 25/4, since the negative sign disappears when we square a number. For the second term, 25 times 1/4 equals 25/4. So our equation becomes 25/4 minus 25/4, which equals 0. As with our first solution, the left side equals 0, which matches our right side. This confirms that x equals -1/2 is also a valid solution to our quadratic equation. Through our substitution and verification process, we've confirmed that both values satisfy our original equation. This process demonstrates the importance of checking your answers when solving any equation. Therefore, the solutions to our quadratic equation are x equals 1/8 and x equals -1/2. Both values make the original equation equal to 0.